All right, let's get into it. We're going to talk about how an artificial brain, a neural network, actually gets smart. The thing is, they don't just come out of the box with all the answers. They have to learn by messing up, over and over again. Which, when you think about it, sounds a whole lot like us, right? But here's the big difference. We learn from our mistakes using, experience, intuition, gut feelings. A neural network? It does it with pure, cold math. So that's the real puzzle, isn't it? How does an AI look at a mistake it made and then, just using numbers, figure out how to adjust itself so it does better next time? Okay, so to really get this, you only need to wrap your head around two main parts of a neural network. First up, you've got the architecture. That's basically its fixed structure, all the neurons and how they're connected. Then, and this is the important part, you have the weights. Just picture thousands, maybe millions of tiny little knobs that you can turn to tweak all the calculations happening inside. So it follows that if a network messes up, it's almost always because its weights, those little knobs, are set to the wrong positions. And this whole process, this massive task of finding the perfect combination of settings for all those knobs to make the fewest mistakes possible, that's what we call optimization.
All right, theory's one thing. Let's make this real. We're going to walk through a super simple everyday example to see exactly what this optimization thing looks like in the wild.
So, let's say you're the manager of a local swimming pool. Your big headache is figuring out how many lifeguards to schedule each day. You've got all the data from last summer, and it's pretty obvious, right? The hotter the day, the more people showed up. The cooler it was, the fewer people came. The big goal here is to use all that old data to make a smart guess about the future. So, what does a computer do? Well, it starts by doing something that sounds kind of dumb. It just draws a completely random line right through the middle of all your data points. Then comes the important part. It has to measure just how wrong that random line is. And it does that by adding up the distance from the line to every single data point. That total distance, that's the error. From there, the whole game is just to tweak that line a tiny bit at a time, again and again and again, trying to make that total error as small as it can possibly be. And eventually, after all that tweaking, it lands on one single line that fits the data better than any other. This final, perfectly optimized line has a name. It's the line of best fit. And for a simple problem like this, it's the best prediction tool we've got. But life's never that easy, is it? What happens when things get more complex? It's not just about temperature. What about humidity? Or what if it's raining? Or if it's a Saturday versus a Tuesday? All of a sudden, our neat little line on a simple graph it's not going to work anymore.
See, every time we add a new factor, like humidity, we add another dimension to our problem. Our simple line might become a flat plane. Add another factor and, it becomes some bizarre multi-dimensional shape that we humans literally can't even picture in our heads. And this is exactly where neural networks start to shine.
Okay, so to get a handle on how a network actually deals with this crazy multi-dimensional problem, we need a better way to think about it. So let's ditch the swimming pool for a minute and try a metaphor. Let's imagine our AI is an explorer on a quest. Here's how this quest works. Picture all those thousands or millions of weights in our network as coordinates on a giant invisible map. And at any point on that map, the altitude, how high up you are, is just the size of the network's error. The higher the altitude, the bigger the error. So the goal of the quest is pretty simple. Find the absolute lowest point on the entire map. So we start by just dropping our little AI explorer at a completely random spot on this map. That's the same as setting all the weights to random numbers at the beginning. Now, the explorer is blindfolded, in a way. It can't see the whole map. The only thing it can do is feel the ground right where it's standing, figure out which direction is the steepest way down, and take one tiny step. Then it stops, checks again, and takes another step. And it just keeps doing that over and over and over. Sooner or later, our explorer takes a step and realizes, wait a minute, every single direction from here is uphill. It must be at the bottom of a valley. It's found a solution, but, and this is the million-dollar question, is it in the deepest valley on the whole map? And this right here perfectly explains a huge idea in machine learning. The explorer might have found what's called a local optimum. Think of it as the bottom of a little ditch. Yeah, it's a low point, it's a pretty good solution, but it's not the best one out there. What we're really hoping it finds is the global optimum, the absolute lowest point in the deepest canyon on the entire map, the best possible solution. Okay, so this whole explorer story is a great way to think about it, but how does it actually connect back to the nuts and bolts of training the machine? Let's bring this metaphor back down to earth and talk about the actual algorithm that's doing the work.
Well, that whole strategy, the explorer looking at the ground and finding the steepest way down, that's all powered by a really famous algorithm called backpropagation. What it does is it looks at the final error, the final mistake, and then it works its way backwards through the whole network, assigning a little bit of blame to every single one of those weights. Once it knows who's to blame, it just gives each weight a tiny nudge in the right direction, the direction that points downhill.
Now this is where it gets really clever. Over the years, engineers have come up with all these tricks to keep the explorer from getting stuck in one of those shallow valleys. For example, you can just start with a bunch of explorers in different random places and see which one finds the lowest spot. Or, if you've got a powerful enough computer, you can have a whole team of them searching at the same time. You can even change the size of the explorer's step, making it big enough to sometimes just hop right over a small hill that might have trapped it. And that step size we've been talking about, it has a proper name. It's called the learning rate, and it's a super important setting. It controls just how big of a change the network makes to its weights each time it learns. If you make the learning rate too big, your explorer might just leap right over the deepest valley. But if you make it too small, it could take, well, practically forever to get to the bottom.
But here's a twist. Let's say everything goes perfectly. Our explorer is a genius, it uses all the best tricks, and it finds the absolute, undisputed lowest point on the map, the global optimum. You'd think we'd be done, right? Well, not quite. The job is only half finished, because now the AI has to face its final exam. Here's the problem. It is entirely possible for a network to get too good at learning the data you give it. It can become a master at just memorizing the answers for the specific examples it's seen, without ever actually understanding the rules behind them. Think of it like this. It's like someone who studies for a test by just memorizing the answer key. Sure, they'll get 100% on those exact questions, but they haven't actually learned a thing.
And if you have enough data, you will always find weird, random coincidences. I mean, believe it or not, there is a real, measurable correlation in historical data between the divorce rate in the state of Maine and how much margarine people ate across the US. It's totally meaningless, but the numbers line up. And neural networks are dangerously good at finding these silly little connections and treating them like they're some kind of fundamental law of the universe.
This very specific danger has a name. It's called overfitting. It's what happens when the model doesn't just learn the patterns in the training data, but it also learns all the random noise and all those weird coincidences. It learns it so perfectly that when you show it new data it's never seen before, it just completely falls apart.
And that's why training an AI is really more of an art than a pure science. It's not just about running the math. The best way to avoid this overfitting trap often comes down to human judgment. Keeping the model simple, being really careful about what data you feed it in the first place. It's about thinking ahead about what features actually matter and trying to guess what kind of dumb mistakes the AI could make out in the real world.
So all of this leaves us with a really big final question we should be thinking about. When we train one of these AI models, when we optimize it to get the absolute lowest error possible, are we actually teaching it to understand the world? Or are we just getting really, really good at teaching it how to pass the test?